Hi everyone, and welcome to the presentation of the Electric Drive Demo Kit, EDDK. Firstly, I will talk about the structure of this product. Then we will look at the software features, and finally we'll see an example of how it works. Let me start by giving you some background information. In this figure, we can see how it looks like. It is a completely enclosed demo kit composed of the control board, which is based on the PED-Board V3 fully programmable by LabVIEW, the adapter board, a silicon carbide inverter with integrated sensors like current, voltage, as well as temperature, and two permanent magnet synchronous machines. The first one is acting as motor and uses a resolver as position sensor. The second one acts as generator because there are resistors connected to the stator winding. Let's move on to the front panel. Here, on the top right corner, we can see a chart that will be used to show the measurements and quantities acquired by the FPGA. This is a synchronous scope, which means that each sample acquired by the FPGA is shown here. The complete control loop is based on the field-oriented control, and it is entirely closed on that FPGA using single-precision floating-point arithmetic. The project is available and open to customers, so you can see how the field-oriented control is realized and how it works. The software provides some indicators to help user. On the left of the chart, we can see the speed, the inverter modulation index, and the DC link bus voltage, which is now around 300 volts. On their left-hand side, we can see the speed and the torque control that allow customers to provide the speed or torque reference. Moving to the bottom left corner, we can see the temperature of the silicon carbide MOSFET power module, the resolver errors indicators as degradation of signal and loss of tracking. Near to them, there is the FPGA heartbeat, which blinks when the FPGA is running. The inverter switching frequency and the field-oriented control execution time, which is around 11 microseconds. This is the angle outage required to align the resolver position sensors, and it must not be changed. On the bottom, we can see the real-time target section that represent microprocessor's loop rate, which is around 1 millisecond, and the execution time. The scope on the bottom of the chart can be enabled or disabled in order to see the quantities. Then there are other indicators displayed like the currents on ABC stationary reference frame, the ID, IQ on the synchronous reference frame, and as well as the DD and DQ, which are the normalized quantities of the output of the current controllers. Let me show you now how it works by pressing the PWM on button and setting the speed because we're in speed control mode. We can set it to 400 RPM, and as you can see, the tachometer indicates the updated value of speed. This is instantaneous. The yellow signal shows the speed, and its accuracy is around 1% at full scale. We are around 29 RPM. So, now we can freeze the scope pressing on the related button. The black signal shows the DC link voltage, and we can find it on the legend place on the bottom right of the chart. These signals on the center are the phase currents. In particular, blue is IA, red is IB, green is IC, violet represents the Q-axis current, and grey the D-axis current. The load factor now is pretty low, so we can see some distortion on the phase currents. This is proportional to the speed because there are some resistors connected to the stator winding of the second electrical machine. Enabling the scope and reaching a speed of 900 RPM, we can see that now the load factor increases. We can stop this test, and also we can use the chart's features to zoom on the signals. This is the sync of the scope. It is not real. The scope is refreshing the image at this point. When we do a zoom out, the chart will perform an autoscale based on the speed, current and voltage. In this way, we can change these scales and reset all the desired values. Removing the other quantities, we can see very well the currents. This is the IQ, this is the ID, and these are the phase currents. We are using a real electrical machine, so what we can see is that there are non-idealities in the currents as distorted waveforms. We can bring the scale to the original values by setting here 1500 samples and here 0. This is the full scale because we are 1500 samples on the scope. As we can see, the temperature will rise very slowly even if the system is working for hours. We can decrease the speed. And we have to take a look at all of the software features. Thank you for your attention. The following preview has been provided by ED Elettronica Dedicata. For more information about this product, take a look at the sites below.